Good morning, everyone. Uh, well, I guess I don't need an introduction. Ellie did a great job. Not gonna lie to you, public speaking is not a thing that I'm used to, so I'm gonna be a little silly for a second. I actually wrote a theme song for my presentation. Crazy, right? Um, so if anyone knows like the kind of theme song to the Fresh Prince of Bel-Air, that's kind of what I was going for. Okay. Um, Now this is a story all about how OECI came to show out, and I'd like to take a minute, just sit right there to tell you how I became a scientist in that New England era. All right, I'm feeling a little better now. So over this summer, I spent my time in Rhode Island, first time being there, and it was great. So my project was on the spatial and seasonal distribution of air sea CO2 flux in the Narragansett Bay. I know that title sounds overwhelming, but we're going to get into it. All right, so just a little overview of my presentation. I will be kind of telling you the importance of studying air sea CO2 flux within the Narragansett Bay. And my data source is the Narragansett Bay Fixed Station Monitoring Network. That's where a lot of my figures came from. My results and discussion, which is the seasonal and spatial variability in the flux patterns that you'll see. And the conclusion, just the key findings and the implications, like why did I do this? All right, so just a kind of wide overview of the ocean, the deep blue sea, really. The ocean plays a really important role in absorbing and storing atmospheric CO2, and that's acting as a global carbon sink. So, how does this affect you? It affects you even if you don't necessarily live near the coast. So it affects you during with climate regulation, regulating global temperature, food security. I know I myself love a good seafood boil, crawfish and catfish. And, because of this, seafood may become more expensive or scarce. And of course, air quality. Everybody take a deep breath in. Yeah, we need that, right? So just, a healthy ocean chemistry is healthy plankton, so the biology within the ocean, and that in turn means healthy oxygen for everyone. Realized I put the clicker down. All right, so kind of magnifying where my study site was, it was in the Narragansett Bay. And coastal areas similar to the Narragansett Bay are actually hotspots for carbon exchange, really because we live on the land and sometimes we the problem, y'all know. But it is due to runoff, pollution, and land-ocean interactions. So my project goal was specifically to determine if the Narragansett Bay was a CO2 source, which means it absorbs CO2. I'm sorry, if it means it releases CO2 back into the atmosphere, excuse me, or CO2 sink, which means it absorbs and stores CO2. And by doing that, I identify the major factors that control CO2 flux within the bay. All right, so if you turn your attention to the greenhouse gas emissions data set, you will see that we have transportation, residential building, electrical consumption, commercial buildings, industrial processes, industrial buildings, natural gas distribution, waste, and agriculture. The Narragansett Bay is omitted from this data report, which will be a very important piece to my project as we continue. So basically, this is the Narragansett Bay. If you turn your attention to the left, the figure to the left, you'll see a wider scale of basically where it is and where it sits in Rhode Island and next to Massachusetts. And then if you look at the figure to the right, you'll see the sub regions monitored all the way from 99 to the uh, 2020, 2022 to 24. Now, what's being measured? So basically, the key parameters are the temperature, salinity, dissolved oxygen, chlorophyll, and pH. These were measured in a 15-minute interval in R. So if you look at the plot at the top of the screen, you'll see the correlation between the key parameters, like how pH and chlorophyll change and change with DO, giving more insight into the biological and physical insight within the water chemistry. And then if you look at the bottom equation, this is how to get total alkalinity, which we'll go into our equation shortly after this. But basically, it is 477.62 plus 51.99 times salinity, and that is our total alkalinity equation. Now, moving forward, this graph, really colorful, right? I'd say it almost looks like an abstract painting to me. It shows across the year the different monitoring sites, which you'll see the different colored lines kind of correlate with the sites at the top where the map is. And the dots right in the background show the individual sensor measurements, which are pH, salinity, temperature, and the estimated total alkalinity, which we reconstructed to see the FCO2 distribution within the Narragansett Bay. And the x-axis, we have the day of the year, and in the y-axis, we have the FCO2 distribution. And if you look right between, I know that you can't really see like what day 200 is or what day 300 is, but if you look between 100 and 300, that is going into the spring and summer months, and you see the different variations going on within the different sites. Now, here's the big equation, which really gets us to calculating the air CO2 flux, and that just tells us whether or not the ocean is absorbing or releasing CO2 into the atmosphere. And with this, the gas transfer, we used a 6 meters per second for this project, and it was calculated in CO2 system in our studio. All right, now for the big reveal, we have the monthly CO2 flux. So from January to April, you will see that in the upper bay, that red dot right there, that indicates that it was a positive flux, which means that it's emitting CO2 into the atmosphere. And that is near the Providence area, so it is a CO2 source in the upper bay. And that is due to respiration and sewage discharge, which was a really big thing in Rhode Island. And in the lower bay, you'll see that it is a sink and it's mostly neutral. So I know you probably aren't really able to see the white dots, but they're there. And that just means that it's neither a net source or sink within that area. And being a sink, as you'll see the purple dots kind of purplish, the cold water has a higher solubility, which means it holds more CO2. Now, moving along the year, you'll see the colors change. From May to August, it's getting warmer outside. So in the upper bay, you'll see that more of a high flux with a lot stronger emissions in CO2 during those summer months. And then in the lower bay, it does still remain a net CO2 source, but generally lower, but still emitting. And that releases across the same period. All right. So moving into kind of the end of the year, still kind of warm outside, but getting a little cold. You'll see it still consistently shows that high flux, especially near the Providence area. And that indicates that even in the late fall and early winter, it still serves as a CO2 source. And in the lower bay, you'll see a moderate to low emissions, suggesting that it's still weaker. It's weaker, but it's not as also not as significant, but the uptake is still observed, and it still remains a source. All right, so back to that data set I was showing you all earlier in my presentation. You will see that if the Narragansett Bay was added, which it should be, it will produce zero point 0.1 to zero point 0.2 million metric ton of CO2 to the atmosphere, which is very important to have in this data set because it's a contribution. All right, so my conclusion is basically our findings show that the Narragansett Bay is a source. It's contributing, unfortunately. Now, the bay's CO2 flux is driven by an interaction of physical, biological, and chemical factors, including temperature and stratification and the balance between photosynthesis and respiration. Now, quantifying these processes is very essential to improving the carbon budgets and assessing regional climate mitigation efforts in all coastal areas, not just the Narragansett Bay. Now, again, what's next for the future? Future studies should fill in the data gap, fill in those knowledge gaps for other coastal areas, like I said, by better understanding CO2 flux dynamics, which are essential for accurately measuring carbon budgets and creating effective climate regulation policies. All right, here are my acknowledgements. Thank you to all of the program coordinators. Y'all are absolutely amazing. Noah, OECI, y'all can, put me on for that rap right there. I made that, call me. The illustrious Tuskegee University, the University of Southern Mississippi, of course, my project mentor, Hongjie Wang. We had some great conversations. The University of Rhode Island Graduate School Oceanography, where my research was conducted, the Ocean Exploration Club, and everybody for listening. Comments, questions, concerns? All of the pictures that were on my background slides, I actually took throughout time. Thank you so much. And these as well. I really loved Rhode Island's architecture. It was great. Any questions for me? Yes, let me know.
That was a great presentation.
Thank you.
Your photos are fabulous. I was noticing them all throughout.
Thank you.
You really have a talent there. So
Try.
this topic that you're working on
Mhm.
is huge. I hope
agree.
you realize the impact that this research has on kind of the vision for the future when it comes to emissions. And obviously the waters are a big piece of that. And so understanding
Absolutely.
this dynamic is important. I have two questions that kind of go together. Number one, you said that it was the sensors were measuring for 15 minutes.
Mhm.
And I'm wondering if they measured at the same time of the day, because I know you can have fluctuations in how bacteria and phytoplankton operate depending on what
Right.
time of day it was.
Mhm.
So I'm wondering if you know if they measured at the same time of day and why that time was chosen. That's number one. And then number two is, do you by chance know how, what is expected in open ocean as far as a CO2 sink or source? And I ask that because, that area also has a very large open ocean
Right.
piece related to it. And so I'm just curious if you know. I don't. So thank you.
Well, to answer your first question, I am actually not completely sure, and I will find that out for you, reaching out to my mentor because I want to know too. And to answer your second question, globally, the ocean is a sink, but because of those data gaps from different coastal areas, because coastal areas really contribute to that runoff, like in the ocean. So that overall is what's kind of the issue. Not having that data is it's a pushback, but overall the ocean is a carbon sink. Thank you. Am I giving this? Oh, yes, I'm so sorry.
Hi. Great presentation.
Thank you.
Do you know of any ways or are there any ways being discussed to mitigate bays, I guess, in coastal areas as a source?
Um, I would actually love to know, in all honesty, because I want to contribute to that as much as possible. But I really feel like it's just getting that knowledge out there, making sure that people are aware and they know what is contributing to that CO2 flux.
Right. Cool. Thank you.
Thank you.
Great job, Kaila.